Hi, this is Group 13 and our project is Cerberus, a self-propelled robotic car with voice command and object recognition. Our team is formed by Jorge Bulnes, Paula Londono, and Ryan Penland from Computer Engineering and Dylan Rivera from Electrical Engineering. There are many robotic cars that are self-driven. For example, the Roomba vacuum designed to collect trash, or the self-driven lawnmower so you don't have to do the work. Many of these devices have been commercialized and have the capacity for path rerouting or obstacle avoidance. Adding a voice command to these self-driven cars is a feature that allows the car to move and take directions from someone speaking to it. However, most of the existing projects are either prototypes or for very expensive specialized purposes. Our group would like to combine obstacle avoidance on a self-driven car with voice command and object recognition. There are not too many instances of research and current projects involving the combination of these three elements. Our main goal is to build a functioning self-driven robotic car that can move front, back, left, and right with the capability of following a basic and specific voice command related to directions and or providing a voice command to activate the self-driven car so it can find an object. We must successfully apply machine learning and algorithms to be able to achieve our results. We also have a list of specific goals for each mode of the project. First, we want to build a self-driven car able to avoid obstacles. Second, we want to add voice command features for directions and for initiating the self-driven car. Third, we want to add the capability to the car of finding an object from a pre-programmed list. Here we can see a list of our engineering requirements. The three we selected for our final demonstration are highlighted.
For this part, we have the hardware block diagram. This is where all the components are connected together. This happens specifically in thank you to the microcomputer unit, in this case the Arduino. There's a power supply which provides the power to the sensors, the motor driver, the motors, and every other component. Thanks to the microcomputer, which is the SD2 Nano, we can have the image recognition, which communicates through the microcontroller to the voice command. All the things together connect, and we have the final result, which is the autonomous robotic car. For this part, we have the software block diagram. In the IDE, we have the libraries, the algorithms, and the programming languages. In this case, we have Python, and we also have the Arduino, which is a IDE for the microcontroller, which is C++. And when you combine all these things together, we have the simulation, which let us simulate what it will look once we output that to the robot. We have the communication, which the Jetson Nano communicates with the microcontroller. And we have the integration. This happens when we make communication established between all the components, and we can actually see how they all work synchronized, communicating with each other to do different uh, actions. We want to achieve a perfect synchrony between all of them.
From the beginning of the project, we decided to use a small two-wheel chassis to keep the car small because this helped with the car's navigation and kept us within our budget. To open more space, we decided to add two more levels to the original chassis. In this way, the first level was left for power, PCB, motors, and distance sensors, the second level for our microcomputer, and the third level for microphone and camera. The biggest variation we did to the original design were plexiglass enclosure with doors in every side to have easy access to the hardware. And second, the location of the microphone, since we had to change it for one that the user holds to avoid interference of background noise when saying the commands. The system design diagram shows the way Cerberus works. When using voice commands for directions, the car follows the directions that the user provides. If the user says forward, the car moves forward. If the user says turn left, the car turns left. The other mode is when the voice command initializes the self-driven aspect of the car. And while it avoids obstacles, the camera scans the area to find the pre-programmed object. Once the object is identified, the car stops.
Chassis, wheels, and motors. For our project, we decided to design a simple, reliable, money efficient, and effective car. We had to keep in mind the weight of every component on our car and also the movement because we chose to have two motors on the side with wheels mounted on them and also a wheel in the back that rotates 360. We chose these motors because of the power consumption and reliability. Wi Fi. Communication is essential for our project and it will help us achieve our goal. The chosen device to use for this function is the 8265 AC and GW instead of the Edimax because it has both Wi-Fi and Bluetooth on it. It is easily connected to the Jetson Nano and it has very good specs that meet our requirements. It has also proven to be one of the most reliable in the Jetson Nano community. Distance sensors. If you compare all of these sensors, the ultrasonic, the lidar, and the infrared, you can see that the ultrasonic is the best option for our project. It is cheaper, smaller, less heavy, can still achieve high frequencies and a fairly decent distant range. We have to keep in mind that they are one of the most used sensors in the market for obstacle avoidance, making them more reliable. Microcontroller. The Arduino has something which the Raspberry Pi doesn't, which is analog inputs that use constant signals and the voltage as a means to communicate data. Also, users can access thousands of Arduino libraries. What this is packages of code that can be imported into the program to provide extra functionality. Also, we chose the Arduino because it is easier to connect to the Jetson Nano and it helps us achieve obstacle avoidance because of its integrated Omega chips that I will talk more in detail when I go to the PCB design.
For the microcomputer, it was an obvious choice which one we were going to choose. It was going to be one that had a powerful GPU between the NVIDIA Jetson Nano and the Jabun Jetson Nano. The Raspberry Pi 4 was not a good option since it had no GPU. We needed something that was powerful enough that could handle the image recognition part. When we compared the NVIDIA Jetson Nano and the Jabun Jetson Nano, we see that the specifications are the exact same. They don't have any difference at all. And the main difference that they had was the price. The NVIDIA Jetson Nano had a price of $469 compared to the Jaboom, which had a price of $199. This made a huge difference. We had a limited budget, and when we compared both of them, we saw that they did the exact same thing. So we ended up going with the Jabun Jetson Nano. For the microphone, we went with the Lavalier G35. It had noise cancellation and noise suppression. As you can see in the picture, we have a wireless mic that connects to a receiver. This receiver helps with the wireless aspect since it doesn't have Bluetooth nor Wi-Fi. It connects directly with the receiver. This is good since it connects to the voice recognition module and we can be far away from the robot and keep giving it commands. We can use our wake word, we can use the direction voice command, and this is really efficient. That's the reason why we went with this specific microphone.
The Raspberry Pi V2 camera module was a fantastic choice for our car. The camera itself has built-in drivers to the Jetson Nano, making integration seamless thanks to its IMX219 sensor. It is capable of up to 4K resolution, but it's stable at 1080p with 30 frames, or even better at 720p with 60 frames. This module is affordable and easy to work with thanks to the large community support.
PCB schematic. The goal of our PCB is to control the motors and the sensors. Our main microcomputer is the Jetson Nano. From research, we know that the best way to connect and communicate with the Jetson Nano is the Arduino. So for our PCB, we decided to build an Arduino with an L293D chip interconnected to control the motors. How this works is that the Arduino has two main chips. As you can see here, one is the Atmega 328P, which serves as the brain and is in charge of executing the user's program code, interacting with the input/output pins, managing timers and interrupts, and communicating with other devices via serial communication. The other chip is the Atmega 16U2 and is in charge of the USB to serial converter on the Arduino board. It is responsible for converting the USB signals from a computer into serial signals that the Atmega 328P can understand and vice versa. Here on our first PCB schematic page, you can see we have our two Mega chips communicating with TX and RX, and also we have a couple of voltage regulators and our USB. On our next PCB schematic, you can see we have our input jack and our voltage regulator converting this to 5 volts and 5 volts to 3.3 volts. We also can see here the L293D chip, and this one is in charge of controlling the speed and direction of our DC motors. And this chip can also drive up to 2 DC motors bidirectional, which is the amount we need. And also here you can see our sensors. PCB footprint routing and 3D model. So what I used to do my PCB board was Altium Designer. Altium Designer can check for errors in the schematic, and then when I realized there were no errors, then I transfer them to the PCB footprint. To do this, we need to know and make sure that every component has its exact footprint. And then next, I put them all on our board, take measurements, and interconnect them all, route them. And also I used 4 layers because of the complexity to connect them. 4 layers was easier to connect everything. And after that, I checked if there were any errors, and I proceeded to order the board. Also here, I can view this in 3D. From here, you can see our completed PCB board. So I received the board and all the parts ordered, and then I soldered all of them carefully. After this, we proceeded to test it. To test it, I connected the USB port, and I saw two LEDs were lighting up, and also I checked my power system. We have 2 lines, which is 5 volts and 3.3 volts, and we checked it all around our board, especially our big chips, to see if we were receiving the power we needed, which was good. The PCB challenge was that the board wasn't being recognized by the computer. The approach we took to solve the issue was to download certain drivers so that we can recognize our new device. We also changed the Atmega 16U2 chip, which is in charge of the USB to serial conversion. And after I did this, we still weren't able to recognize the device to program it. So our next PCB solution was to build a PCB that interconnects sensors, motors, batteries, and Arduino from our original PCB. Power system challenges. Our main microcomputer, the Jetson Nano, had to receive also power. We thought that connecting the Arduino to it via USB was enough, but it wasn't enough voltage to power it on. We had to use the power jack 5-volt voltage line to connect it. So the approach to solve this was we soldered a 5-volt voltage regulator on our PCB, and we also soldered a power jack cable from that line and connected it to the Jetson Nano. This solution was working for a couple of seconds, but it turned off because the Jetson Nano doesn't do well with voltage fluctuation, which is very minimum, but it still was enough for it to turn off. So because of the time constraint we had, we decided to just connect it using a cable.
Cerberus navigation system consists of 2 wheels attached to 2 DC motors connected to the PWM pins of our microcontroller to control the speed. Since we used three sensors, we connected the trigger and echo pin together to help us save space in the available microcontroller pins to avoid paying extra for additional parts. Each sensor has a range of 30 degrees coverage, which means that about 90 degrees are covered by the sensors. This brings the challenge of covering objects to the immediate sides of Cerberus. To solve this possibility of crashing that way, at least one more distance sensor should be added to each side of the car. We decided not to do it mostly because it will increase the size, weight, and total cost of the project. Additionally, obstacles less than 6.5 centimeters tall might not be read by the sensors if they are very close to them. Regarding the turns, they are activated by using a delay in milliseconds. The challenge is that the delay duration and the acceleration of the motors must be adjusted based on the type of terrain and the input voltage that varies based on the battery charge. An advantage of using DC motors is that to control the direction of the wheels, the motors use an H-bridge circuit. To just by changing the pin values to high and low, we can manipulate the direction. Another advantage is that they connect to pulse width modulation pins to control the speed of the motors. So if we want them to go full speed, we use 100% of the duty cycle, which corresponds to the maximum amount of input voltage. To decrease it, for example, by 50%, we lower the duty cycle by 50%. The problem we found is that when the batteries are dying, the speed gets affected. Additionally, the speed varies based on the terrain being used. Because of this, we face the challenge calibrating the wheels because the one motor seemed to go faster than the other. And based on the battery charge of the flooring, the speed of each individual motor had to be adjusted. So sometimes the car will go straight and sometimes it will not. To solve this, we found out that a gyroscope like the MPU 6050 could be connected to the car. We tried to implement the optimizing navigation, but we had some debugging issues that were taking the time of more important corrections to finish the project, so we decided not to implement it now since our goal is to get the car to move forward, not straight.
For the voice command system, we end up using the Arduino Voice Model Recognition V3. This is a great device since it's really great when it comes to the compatibility with the Arduino. It also has a library which gives us the ability to train different voice commands and then execute them in the code. One of the things that was really great about this little device was that it doesn't use speech to text in order to do all the different voice commands that you want to do. What it does is that the library train the voice and treats them as registers. Then these registers get stored, and when the register identifies that the keyword is being said, it allows for the voice command to do that specific action. The voice command challenges and successes. Well, it was not really great when it came to training the model when there was noise in the environment. We see that it had a lot of failed attempts when we wanted to train the system. Another big challenge was that it only has seven uh, voice commands that can be used at a time. You can store 256, however, to use them at a time, that was a big challenge since we wanted to add more voice commands. The accuracy may suffer a little bit when you have background noise. So we tested it when we were trying to use different voice commands, and when there's too much noise in the UCF campus, we could notice that this suffered a little bit. The successes that we end up finding about this was that the training was successful. When you were in an isolated place where there was no noise, the training was pretty quick. It was really accurate. It was very good. The voice commands respond really, really quick.
What you can see here is the image recognition system, how the whole process works. The Raspberry Pi camera module will capture an image where it will be sent through the object detection model on the Jetson Nano. Anything that is detected will be stored to a variable within the Python script we're running, and it will iterate through detections in each image, as there can be multiple. While that's going on, the Arduino code on the microcontroller will constantly pull for serial data to receive from the Jetson Nano. Once the script recognizes a key object, it will establish a serial transfer of that object to the Arduino, where it will be checking if the desired object matches what we want to be captured, in which case the Arduino code will kill the motors, making the car decelerate and stop. One challenge we faced when trying to get the object detection to work with Cerberus was achieving a stable frame rate. If the Python script was too slow, the camera would have a hard time detecting objects as it would freeze while detection's processed, causing a slower frame rate. A solution we had to this was to lower the quality of the camera to 720p, which still allowed for sufficient object detection to meet the needs of the project. We also had to modify a built-in sleep timer to help stabilize the frame rate between each detection. A couple of successful approaches would include coding our serial communication with the Arduino, making sure the Arduino would handle the constant serial polling between instructions. We were also successful in making sure our objects were detecting accurately and with a sufficient confidence level so that it wouldn't get confused with a different object. These were the softwares we used, the biggest of them being TensorFlow for machine learning models, Python for scripting, OpenCV for camera capture, Jets and Jetpack for the TensorFlow libraries such as CUDA and CUDA-N, and Arduino for the various commands of the vehicle.
For the constraints, we make sure that we follow all the constraints that we have when it came to the economic, environmental, social, political, ethical, health and safety, manufacturability, time, and sustainability. When it came to standards, we have two main standards: related standards and safety standards. For the related standards, it has the impact of the USB on the design, the camera serial interface, and the impact of the CSI on the design. We wanted to make sure that it follow all the protocols. For the safety standards, it's all about safety. We included a braking system. We also have the awareness barrier devices, which if someone comes in the way, the car is gonna back up since it can recognize humans. It has audible and visible warning systems, and it has the control devices. We have a little switch that in case that something fails, we can turn off the switch and cut power to all the system, making it safe in case that something end up going wrong.
The project budget was given to us by the Electrical and Computer Engineering Department here at UCF. We were grateful that all of our initial parts were covered by this budget. As you can see here, this is a table with the costs associated with the project. A lot of inflation within the electronics industry caused a concern when ordering parts, so we had to find ways to optimize our project in order to meet our budget needs. Our predicted price was about $320, but with as much optimization as possible, UCF was kind enough to cover our expenses up to $427. Our project management tools are seen here. We had text message group chats which helped stay in contact with each other at a moment's notice. We kept a Discord server where we stored all important documents and resources to guide us on this journey. To coincide with that, we used Google Workspace applications such as Docs and Sheets so that we could all collaborate seamlessly. We also used Microsoft Office in order to format our documents more efficiently.
Working with this group of people was a great experience. Jorge was mostly in charge of the voice command and then worked in integration of voice, image, and navigation. He also helped with the additional chassis parts and was our video creator. Ryan specialized in machine learning, and then he helped with the integration of voice and navigation as well as the wireless communication. Dylan was in charge of the PCB, which includes all connections between power supply and all components. He also helped with the construction of our first physical prototype and assisted fixing electrical issues that happened during the semester. Finally, my job was the car's navigation. This includes simulations, building the second prototype, and putting together the final car. Additionally, I worked with the creation of the added chassis parts and hardware maintenance. Also, I aided during the creation and integration of project components and was the project manager taking care of deadlines and other administrative tasks.
These are our future milestones. We would like to improve our machine learning model. We want to increase the accuracy of the detected objects. So far, the best accuracy that we could achieve was 89%. we would like to achieve a 98, 99% of accuracy. We want to add more objects that servers can recognize, and once it recognizes them, it can stop or do some more actions. For the voice recognition, we would like to be more flexible when it comes to different methods. We would like to use a different system for time constraints. We were not able to do that. We would also like to add more movement, like angle based movement, in which you could say move 80 degrees, move 60 degrees to the right, move 40 degrees to the left, and it will execute those commands. And this time we want to make servers work without a power cable cord, which was obnoxious and it was not the most optimal solution. However, it was efficient for what we had at the time. Thank you very much.